Let's practice on another problem using divergence theorem to evaluate some flux integral. In this problem, we're going to find the outward flux through the surface of the solid in the figure. So the orientation of the flux is outward pointing, consisting with the statement of the divergence theorem. On the other hand, the surface in question is in fact the surface of the solid box. So it's a closed surface enclosing some solid area in the three-dimensional space. So the setting is suitable to make use of the divergence theorem. And know that the vector field is x squared I plus y squared j plus z squared k, which is not too complicated a vector field. And the surface is not too bad as well. Namely, it's actually possible to use the general formula of the surface integral, the flux integral. Namely, we could convert the flux integral into a double integral with the general formula and evaluate the integral. However, looking at this surface over here, we observe that, well, the surface consists of 6 pieces. Each of them is a flat sheet in the three-dimensional space. While it's not too complicated to parameterize those 6 pieces of flat sheet, it would be quite tedious to go this way. Therefore, we consider the alternative approach by using the divergence theorem. Hence, the procedure that we adopt goes like this. What we're going to do is observe that the surface integral that we are working with this outward pointing orientation, it's equal to a triple integral of the solid Q for the divergence of this vector field, where the solid Q is the rectangular box bounded by those 6 pieces of flat sheet. And through computation, we observe that the divergence of this capital F is in fact the sum of the partial derivative of the first component with respect to x, which is 2x, with the partial derivative of the second component with respect to y, which is 2y. And lastly, we have the partial derivative of the third component with respect to z. Hence, we end up with the integrand given simply by 2x plus 2y plus 2z. Now, we could convert this triple integral into an iterated integral. And what we're going to do is just going to be looking at the boundary of this solid. It turns out to be a typical rectangular shape of solid region, and it's extremely simple to recognize the upper and lower limits of those 3 layers of integration. Specifically, if we choose to integrate your function with respect to x, then y, then z, then your component, the integration limit for x is from 0 to 2, and for y is from 0 to 2 as well. Lastly, for z, it's going to be from 0 to 3. So the integration limit for those 3 layers of integration is given by these 3 pairs of number. As for the integrand, after factorizing the 2 from the sum, what we are left with is just x plus y plus z. So through some straightforward computation, again, it is a polynomial in those three variables with the limits of the integration given simply by some constant. So it's a relatively simple integral to carry it out. And our final answer for this iterated integral is 84.